In this video, we'll work an example evaluating the work in a polytropic process. For this problem, the polytropic constant will be equal to the ratio of the specific heats, K. Recall that when n equals K, the process is adiabatic, meaning that we have a process with no heat transfer. Let's return to our piston cylinder from the car engine example. An adiabatic process means that no heat transfer occurs. A true adiabatic process can be envisioned as a perfectly insulated system. We can approximate many processes as adiabatic, even if they are not perfectly insulated. For example, we estimated that the power stroke of our car engine takes place over 0.0075 seconds. During such a short time, little heat transfer occurs, and we can approximate the process as adiabatic. After combustion, the temperature in the cylinder is 1086.3 Kelvin. The pressure is 1852.81 kilopascals. And the volume is 0.2 liters. At the end of the power stroke, the volume is 1 liter. The mass of gas in the system is 0.001189 kilograms, and the ratio of specific heats is equal to 1.4. What is the work done during the power stroke if we assume that the process has no heat transfer? Recall that the work done when a closed system's volume changes can be computed by integrating the pressure over the volume change. We must know the relationship between pressure and volume to evaluate the work integral. For a polytropic process, the pressure is related to the volume by PV to the N equals a constant. An adiabatic process can be described using the polytropic process, with N equal to the ratio of specific heats of the gas. Substituting, we see that PV to the K equals a constant. Solving for pressure, we see that pressure is equal to the constant divided by volume to the K. Substituting into our work integral, work is the integral from volume 1 to volume 2 of P dV. We see that the work is the integral from volume 1 to volume 2 of our constant divided by V to the K dV, which we can integrate directly. We see that work is equal to the constant times the volume to the 1 minus K divided by 1 minus K, evaluated from V1 to V2. Remember from the polytropic relation that C is equal to PV to the K. Substituting, we see that the work is equal to PV to the K times V to the 1 minus K, all divided by 1 minus K, evaluated from volume 1 to volume 2. Multiplying our exponents, we see that PV over 1 minus K, evaluated from V1 to V2, is equal to the work. Assuming that the combustion products behave as an ideal gas, we can write the ideal gas equation for any state of our system. PV equals mRT. Substituting the PV into our work equation, we see that the work is equal to mRT over 1 minus K, evaluated at V1 and V2, which is simply equal to mass times the specific gas constant times T2 minus T1 divided by 1 minus K. We have an unknown T2 at the end of our power stroke. To find it, we write the ideal gas equation of state for the beginning and end states of our system. P1 V1 equals mR T1 P2 V2 equals mR T2. For a closed system, the mass and specific gas constant are both equal. Thus, we can equate the two states by solving first for m times r. We see that mr is equal to P1 V1 over T1. It's also equal to P2 V2 over T2. Solving for the temperature at the end of our power stroke, we see that T2 is equal to P2 V2 over P1 V1 times T1. Our unknown now is the pressure at the end of the power stroke. We can find P2 using the polytropic relation for the process. PV to the K equals a constant. What this says is that P1 V1 to the K is equal to P2 V2 to the K. Solving for P2, we see that P2 is equal to V1 to the K divided by V2 to the K times P1. Substituting our values, we find that P2 is equal to 1,852.81 kilopascals times 0.2 liters divided by 1 liter, all raised to the K, which is 1.4. We see that the liters cancel, and we're left with kilopascals. And so our pressure at the end of the expansion stroke is 194.658 kilopascals. Substituting this value into the ideal gas equation of state, we find the temperature at the end of the power stroke. T2 is equal to P2 V2 divided by P1 V1 all times T1, which is equal to 194.658 kilopascals times V2, which is 1 liter at the end of the expansion stroke, divided by our initial pressure of 1,852.18 kilopascals times our volume at the beginning of the expansion stroke, which is 0.2 liters, all times the absolute temperature, which is 1,086.3 Kelvin. See that the liters cancel, the kilopascals cancel, and we're left with an answer in Kelvin. The final answer is 570.897 Kelvin. Finally, we substitute this value into our work equation and evaluate. Remember, we found that the work is equal to m times r times T2 minus T1, all divided by 1 minus K. This is equal to 0.001189 kilograms times the specific gas constant, which is 8.314 kilojoules per k mole Kelvin, divided by the molecular weight, 28.97 kilograms per k mole, times our temperature difference. T2 is 570.897 Kelvin, and T1 is 1086.3 Kelvin. All of this is divided by 1 minus K, which is 1 minus 1.4. See that the kilograms cancel, the K moles cancel, and the Kelvins cancel. And we're left with an answer in kilojoules, which is a unit of energy or work. The final answer is 0.44 kilojoules. Remember from our isothermal analysis, we arrived at a work value of 0.597 kilojoules. So this is our adiabatic answer. And from our isothermal example, we had 0.597 kilojoules. The isothermal and adiabatic assumptions form the upper and lower work limits for this process. In reality, the process occurring during the power stroke is neither adiabatic nor isothermal. During the real expansion, some heat transfer occurs and the temperature changes. However, the process remains polytropic. The challenge is in choosing the right value for the polytropic constant n. We'll see in the next example how to use n to fit measured data from a real process, and then compute the work. The result will be a value between the isothermal and adiabatic work. In summary, we computed the work of an adiabatic expansion process. An adiabatic process is one that occurs without any heat transfer. To compute the work, we use the integral of P dV. To relate the pressure within the cylinder to the volume, we modeled the process as a polytropic process. We made the assumption that no heat transfer occurred, which set the value of n equal to the ratio of specific heats for the gas. We then integrated the work and substituted the ideal gas equation of state. Finally, we used the ideal gas equation of state and the polytropic relation to find the needed properties at either state of the system. We computed the work and found that the value was less than the isothermal work. We concluded that the adiabatic and isothermal processes form upper and lower limits on the possible work, and that the true value must be somewhere in between. The value for the polytropic constant n that models the true process can be determined through experiment, which accounts for any temperature changes and heat transfer that may occur. That concludes the example. Thanks for tuning in, and have a great day.